Hello everyone. First of all, let me introduce myself. I am Lucas Lezer from the University of w.r.t Brazil. I'm a master student at the same university and this presentation is part of my master thesis. As you can see, I'm one of the co-authors alongside Fabrizio Nembrek, Jean Paul Bardal, and Alceu de Souza Brito Jr. The topic of my presentation would be interesting for those of you who research it or have been dealing with imbalanced data stream mining. Now, this is what we're going to see today in this talk: the introduction, our proposed math, the empirical evaluation with our method, and conclusions and future work. Well, imbalanced data is one of the challenges when we do with classification tasks. Data sets with class imbalance are those where one class outnumbers other classes. This overrepresentation can lead to classifiers which correctly classifies instance from the majority class, while presenting issues to classify instance from the minority class. This phenomenon is present in applications such as fraud detection, oil spill detection, abnormal activity classification, and breast cancer malignancy classification. And well, as you can see, the minority class is very often more relevant than the majority class. In these examples, hard instances involve high costs if not correctly detected. The problem of imbalanced data is present in both batch and data stream databases. In the batch environment, we can query the entire dataset as many times as needed and apply different techniques to deal with the class imbalance. At this environment, we can handle imbalance by oversampling positive instance, by undersampling negative instance, by combining both techniques, or by using ensembles to divide the main problem into balance the sub-problems, and using misclassification costs. However, in the stream scenario is different. In stream environments, the classification tasks becomes even more difficult as no information can be retrieved from the whole dataset because it's infinite. The classifier has only data from the past, and there is no guarantee that the data behave observed, thus shall be maintained. And due to the evolutionary behavior of the data stream, the proportion between classes may vary over time, and new imbalance may arise. In order to deal with imbalanced data stream mining, we used misclassification costs. The idea behind this approach is to assign penalties for classifying from a class in another. It is possible to employ higher costs to the positive classes to make the classifier considered during prediction and training steps. If we have a binary classification task, the costs for each class can be represented by a cost matrix for two classes. Let the function cost in this framework here be the involved cost in classifying example x in I when its ground truth class is j. One way to build a cost-sensitive classifier is to build a model which chooses the class I, which minimizes the sum of the probabilities and costs for the actual class of the example x. As an example here, this model would choose the red Spock hand because it has the higher probability value, right? However, if this model is cost sensitive, it would choose the green Spock hand, not just because the green cost is higher, but the green Spock hand is the class which minimizes the sum of the costs of the alternative classes. This is what we call threshold because we are changing the classifier decision threshold. Another way to induce cost sensitivity to a classifier is by considering the cost as examples weights. That would be oversampling and undersampling by cost. In this talk, you are going to see the impact of the distribution of cost sensitivity in an ensemble of decision trees developed to data stream classification, aka adaptive random forest. We propose the cost sensitive adaptive random forest, CSARF for short, which employs two variations to consider misclassification costs. Well, to handle imbalanced data streams, we already have some proposed solutions. SETA, selective recursive approach, consumes the data stream as successive batches and reuses the positive examples from the previous batches to decrease the degree of the imbalance of the current batch. Both Learn++, CDS, and Learn++ NIE interprets a data stream as successive batches as well. The CDS variation uses both to resample instances that are incorrectly classified in a batch, and a new classifier is trained in this enriched batch and may replace a current classifier. The NIE variation is to train each of the classifiers in balanced subsets. Using misclassification costs, we have here 3 neural networks. The first two use the costs in the objective function. The first one just have this feature. The second use an adaptive cost matrix capable to change the weights whenever concept drift occurs, and the third employ a cost matrix that is optimized by a genetic algorithm during the training step. Well, to understand how CSARF works, we first have to understand how ARFRE works. So, ARFRE, the adaptive random forest, is an algorithm proposed for data stream environments which use the main features present in the popular random forest. ARFRE induces a set of incremental decision trees using online embedding and a limited and randomly selected number of features per tree. Each tree has an individual drift detector, and this is used to handle concept drift. As soon as there is a suspicion of concept drift in the data stream, ARFRE starts to train new classifiers to replace the current if the change is confirmed. The final decision of the ensemble is given by the weighted majority vote, using accuracy of each base classifier as weight. The cost-sensitive adaptive random forest, CSARF, is a variant of ARFRE planned to handle imbalanced data stream. To achieve this, we did some change on the original algorithm. The first change is that each tree is now weighted by its performance on the metric Matthews correlation coefficient instead of accuracy. Accuracy in balanced environments is ineffective in evaluating the performance of a classifier. That's why CSARF uses MCC, which is a great metric to evaluate a classifier in binary imbalanced datasets. The MCC uses all four information from the confusion matrix when evaluating a classifier, and by considering the proportion of each class, it assigns higher values to the classifiers which perform well in both classes. This metric is more popular in machine learning applied on computational biology, which usually deals with imbalance problems. The second and the third change is the addition of a slide window to observe the class distribution over time and ensure that every tree trains with the positive instance. ARFRE does not differentiate the classes when training its trees. This leads to a probability that positive instance will not be presented for some classifiers of the ensemble. By using a slide window, CSARF can detect the minority class locally and ensure that every tree in the ensemble trains with the positive instance. And the last change is cost sensitivity through two different strategies, local and global. This change is based on the use of the cost matrix by changing the weight majority vote in two ways. Use the cost framework. This cost framework that I talked earlier. The first change is the CSARF local, which uses the misclassification costs to influence the output of the basic classifiers before the combination of the votes. This means that every tree's output when predicting an instance is going to be influenced by the cost matrix. After that, the weight majority vote is computed. The CSARF global applies the cost matrix after combining the basic classifiers. In this way, we change not the individual opinions of each decision tree, but the combination of their opinions. The most common way to build a cost matrix is to set a fixed misclassification cost for each class. This cost can be chosen through an exhaustive grid search testing various costs to achieve the desired performance. But in stream environments, this strategy may not work because it doesn't consider the class distribution variation and that the infinite universe of a data string is unknown. That's why CSARF uses a cost heuristic based on class distribution. The PSEC cost heuristic is originally used to oversample positive instance and undersample negative instance based on class distribution, but we use it to change the decision threshold of a classifier. By applying this cost heuristic on CSARF slide window, we can build a cost matrix which is dynamic as data string is, and as data is consumed, the distribution may vary, and as execute, the misclassification cost change as well. Well, in order to run the experiments, we use the framework Massive Align Analysis, MOA, as ARFRE was already available in this environment. We code the CSARF into MOA as well. The experimental protocol consists of evaluating whether the null hypothesis that there is no significant difference between CSARF and ARFRE in balanced dataset is true. In order to evaluate CSARF with similar approaches, we included the ARFRE with resampling in the experimental protocol. ARFRE with resampling uses sampling techniques but without reproducing the information loss present in undersampling or slower training phases caused by oversampling. He combines weights with the Poisson distribution output for a given instance. The higher the incidence of a class, the lower it is the weight assigned to the instance which belongs to this class. We evaluated ARFRE, CSARF, and ARFRE with resampling in 12 binary datasets using the metrics average, F1 score, average recall, and AUCPR. We selected 6 real datasets with different class distribution from low to high imbalance degree, and six synthetic datasets that were generated by the ARFRE and CIA generator with different imbalance degree as well. And finally, we used Prequention to evaluate the 3 models generated by the following parameters. There are some interesting points to highlight here, but let's begin first with the average recall. As you can see, both CSARF and ARFRE with resampling rank the first in almost every dataset. We notice that the performance again is low when evaluating CSARF and ARFRE with resampling on low imbalance data, as in electricity, this one here, and airlines datasets. So you may notice that both versions of CSARF performed even worse than ARFRE in the airlines dataset here. And however, as this is not a problem with a high degree of imbalance, the North class instance is not that significant. When dealing with datasets where is a high cost involved in classifying one class in another, opting for a classifier which correctly classifies the positive instance is crucial. This is clear in the credit, private, and synthetic datasets, where CSARF and ARFRE with resampling performed better, especially CSARF Global, which presented the best performance in the reimbalanced datasets. When evaluating the methods using average F1 score, we noticed that ARFRE presented great performance in some imbalanced datasets. In the contrast to the previous metric, CSARF Local scored the first place in almost every real imbalanced dataset. The global version of CSARF was noticeable only in the synthetic datasets generated by CIA generator, which ARFRE with resampling stands out with the best results. Moving to CPR, which is an interesting metric to evaluate a classifier in different decision thresholds, you can see that ARFRE ranked first in one of the most imbalanced datasets, that is Pozzolo, present a difference around 20% when compared against ARFRE with resampling, but allow difference against the 2 versions of CSARF. This result evidences that the original ARFRE can be used in some imbalanced scenarios if you explore different decision thresholds instead of using the full threshold. Well, we did the NME test to verify if there is statistical significant difference between the algorithms evaluated in each metric. For a confidence level of 95%, CSARF Global is the best among the other approaches evaluated in average recall. It has the first rank here. For this metric, both CSARF Global and ARFRE with resampling presents statistical meaningful difference when compared with the original ARFRE. In the average F1 score method, CSARF local stands out with the better performance and significant difference when compared against the original ARFRE. In this metric, these last three ranks here, there is no difference between the last three ranks. When evaluated the classifiers in the UCPR metric, the results suggest that there is no significant difference between the performance of the evaluated methods. So in UCPR, there is no difference. Even so, CSARF ranked first in each of the metrics evaluated, and the null hypothesis is rejected. The NME test also suggests that between CSARF versions and ARFRE with resampling, there is no significant difference. However, it is unknown the impact of resampling data streams in concept drift detection as ARFRE with resample uses, because the classifier interprets the problem in a different way of its nature. So for those reasons, CSARF can be a better option to handle imbalanced data streams than ARFRE with resampling. In this talk, an empirical study was presented on real and synthetic imbalanced datasets. The comparative analysis between ARFRE with resampling and CSARF made it possible to evaluate the beneficial impact of the use of strategies based on misclassification costs. For future work, the objective is to analyze the CSARF performance for non-binary classification tasks that also present imbalance, and also the use of different cost heuristics that follows the relevant changes of a data stream. Well, have a special thanks because this work here was financed by CAPES through the Fundação Araucária program, and to PPG, the post-graduate program in Applied Informatics as well, and PUC-PR, that is my university. So, thanks.